these things here are all sequential scans. These things, and that's a count of the number of rows. These things down here are index lookups, and the stuff that you're not seeing on here would show you all sorts of updates and deletes and stuff like that. So what this is telling us is the workload on this server is almost all reads. There's very little lead update traffic on this thing, and the majority of the reads that are happening as part of sequential scans of the database. So this is actually not a problem for this database. This is the case because a good chunk of the data that's the most active in the database are tiny tables that always get sequentially scanned just because they're tiny tables, with information, what some people call factor dimension tables, the kind of things you join everything with in order to decode them. So this is not a problem, but when stuff like this pops up, it suggests, okay, let me go figure out at the per table level who's actually doing all of these reads and figure out, does all this sequential access, is that sensible or is it just really dumb this way? Yeah.
Is it possible to see a graph of combining this in photo with so you can see not just the reads but the actual physical reads that occur on distributed?
All this, if you've got a monitoring system, you're not necessarily going to get them all the same graph, but I mean, if you've got them on the same scale, which these two are, you can look at the two right next to one another and try to look for patterns. So I mean, these are graphs of the exact same time period, so we are essentially getting that just by looking at the two graphs. A lot of times the graphs are not actually combined because the scales are slightly different. Like this is measured in buffers per second, the buffers being 18 pages of data. This is measured in tuples, which are rows of the database. So graphing them on the same thing would make sense, but you do want to line them up on time protections. And that goes back to, see, like, if you look at this thing, if I were to overlay on top of the disk I/O statistics, you'd probably see the spike in disk I/O over the same period as well. These are the sort of, this is why you need to monitor at all these layers, and then when events happen, go back and figure out later, okay, what just happened. Long queries. It's possible to go into PGStat activity and ask for what Postgres calls the age of the timestamp. And you can also just subtract what the current system timestamp is from the transaction begin or the query begin timestamps. If you do those, you can compute out of all the things that are active right now, what's the oldest running transaction, and then what's the oldest running query, and both of those numbers are interesting, and they're very interesting to graph over time. So this one is not all that exciting, but it does let us know that there's something that runs on the server quite regularly that's causing this little spikes, where even though the queries are short, something is holding transactions open for 5 or 10 seconds quite often. So that suggests, that's a little strange. Why is it holding the transaction open, but not actually, that's not clear in the query that that's happening? It's a little interesting. And then this thing here, this is the stuff you really want to watch out for. If, in the event of an actual emergency, this seconds would become hours, and this number would be so big that it would dwarf all the rest of the data on it, and that's when you go, oh crap, what has been running in a single transaction for hours, because those are the exact situations where vacuum is going to stop while it's happening. So here's a graph you can do that will show you visually how long an average transaction is and a typical one is, so that when a longer one shows up, it really becomes visible. This same server I grabbed this data on, and then later they had a query that stayed open for 3 days, and vacuum never got cleaned up, and then ran out of disk space. There was a whole cascade of failures. You could trace them all back to, at the beginning, this transaction just started having its time go up and up because it had something that was running for a long time. It should not have been keeping an open transaction. So that's kind of the quick tour of Munin. This is just a subset of the database stuff that's in Munin. And every one of these things I just showed you, out of the box, you get all those graphs. And it's a lot more. So that's why I like it, and I find it inspirational. Query logging. Postgres doesn't really have any good integrated stuff for monitoring queries in the database with it. The main mechanism for getting some of it is there's a parameter called log duration statement. The idea is you set that to how long the query has to run before it's interesting that it ran that way. So fine-tuning that, as I commented before on the auto vacuum one, you have to be careful to make it long enough that it's only showing you interesting data, but not so short that the logs just fill it with junk. Auto-explain, I also already mentioned, if you got this thing on, auto-explain kicks in when this threshold is exceeded. That's when it goes to log all this stuff together. There are basically two ways you can do this. You can write all the data to the log file, and then you go analyze it later. Or you can use something that's built in starting in Postgres 8.4 called PGStat statements. And PGStat statements, you give it a block of memory and you go, here, you can please record statistics about whatever you can fit into this block of memory I've given you. And then it does a best effort way to try to keep the most popular things that happen in that block of memory. PGStat statements tends to not be a complete replacement for saving the data into the query logs because it's lossy. Some of the data gets thrown away. And so I find people end up doing a little bit of both of these to this point. You might get a real-time view of what's going on with the server with PGStat statements, but for long-term analysis and kind of figuring out, okay, what did the server do all day, logging it all through log file and analyzing it is still the best approach that's available, unfortunately. You do need an external tool for that. The most popular of them is a program called PGFluene. What PGFluene does is produce neat bits of output like this. This is the most key thing to pay attention to. This is summing up all of the queries that ran on the server that look like this, and it does some ways to reduce them to get the approximately. So what this is saying is, this first query here, these all executed the same number of times. This is on a PG batch. And I'll steal this example from PG. What this is saying is, even though all of these executed the same number of times each day, it ran just over 23,000 times, the key bit is, on average, this one took almost 300 seconds to run. And this one, the total time on that is way huge. So the way they end up using data like this is, if you got this output, one thing that people love to do is speculate on why performance problems. If you describe a performance problem for a group of people, they'll spend all day talking about, wow, I wonder what could be causing that. I wonder if it's this. I wonder if it's this. What people who do this for a living do is assume that whatever your guess is wrong, and that you're not going to get it right, and do profiling instead. It's actually a measure rate. And sometimes you get it right, and sometimes you go, huh, I didn't expect that at all. So the trick is, when you get data like this focuses you on the things that are really slow on the server. So you might have looked at this, and you might have thought, this update on the branches table here, that's got a lot of contention around locks. So maybe this thing is slow because the contention around the locks are perfect. That would be a completely reasonable theory that you might come up with for why this thing is slow if you were just looking at the transactions. But you'd be completely wrong. It's actually this update here is the thing that where almost all the time is going on this whole thing. So when you get logs like this, the trick is whatever are at the top and whatever the things that are taking the bulk of the runtime up, that's where you got to spend your time optimizing. Because you can, in this workload, you can optimize numbers 2 through 4 all day, and it's going to have almost no impact on the actual performance of the server. If you don't take care of the thing that's at number 1 here head on, you're never gonna make this sort of faster by a query tuning on this particular workload. So for non-trivial stuff, getting this log file out every day and kind of seeing what the trends look like over time is one of those things. It's not built into Postgres, but you really want to start doing it before the server gets slow, because you know what a good workload looks like before it goes bad, and also it gives you an idea what baseline